Like I said previously, electrochemistry is one of the areas where we can get something useful out of our reaction. We'll see exactly what that means in this video today. If we have a setup like this, where we're oxidizing a metal and reducing a metal all in one single beaker, we can't really get something useful out of that. As this oxidation reduction happens, we end up with this bar that's being oxidized, disintegrating over time. And we end up with ions in the solution being reduced to become solid metal. At the end of this reaction, you'll just have a little puddle of copper solid in the bottom as your zinc bar disappeared. The electrons were transferred and the energy was transferred, but it didn't do anything useful. However, if you set up the oxidation and reduction reactions to happen in two separate places, two separate beakers, you can harness that energy to do something useful. You can harness those electrons that are being transferred from one reaction to the other, from one beaker to the other, to do something useful, like turn on a light bulb, for instance. So putting these two half reactions in separate beakers and connecting them by wires and things, that's a galvanic cell. We're going to talk specifically about a Daniell cell. What is a Daniell cell? A Daniell cell is specifically when copper and zinc are the two things that are reacting. So since I know that copper ions, copper 2+, is a blue solution, I'm going to label this solution copper 2+. That's going to make this solution over here zinc 2+. This bar in the copper solution is a copper bar. This bar in the zinc solution is a zinc bar. So if you look up the reduction potential of copper, you see that the reduction potential of copper is 0.34 volts. That reduction potential is representing the reaction of copper 2+, gaining 2 electrons to become copper solid. If you look up the reduction potential of zinc, it's negative 0.76 volts. That's zinc 2+ becoming zinc solid. If you want this combination of half cells to result in a spontaneous reaction, that's going to mean that you need a positive E cell. So how do you arrange these to get a positive E cell? Well, there's a couple of ways you can think about this, and we'll talk about them. But if you use this formula above, where it says the E of the reduction half reaction should be added to the E of the oxidation half reaction. Down below, we've said that the reduction of copper is this, the reduction of zinc is that. The oxidation of copper would be negative 0.34 volts, while the oxidation of zinc would be positive 0.76 volts. Again, we're wanting a spontaneous reaction, so the best way to get a spontaneous reaction is keep the positive one the way it is and change the sign of the negative one. That's going to mean that we want copper to be reduced, it's really Cu2+, and we're going to need zinc solid, to be oxidized. And I know that because I recognize that I need to change the sign of this one, this zinc, in order to yield a positive voltage. So if you add 0.34 plus 0.76, positive 0.76, you get 1.10 volts. The Daniell cell that we've shown here should have a voltage reading of 1.10 volts. Cool? Cool. Okay, so it took a lot of work for us to even figure out that we wanted zinc to be oxidized and copper to be reduced. So let's write the half reactions that are actually going to happen when you connect this galvanic cell. Copper is going to be reduced, and I just erased it, but it's the same reduction half reaction we just had written there. And zinc is going to be oxidized to become zinc 2+. So if we take a few minutes to talk about the setup of a galvanic cell, there are a few things you need to recognize. First, you have to know who's oxidized and who's reduced, and be able to come up with the voltage that the cell should read when you hook those cells together. But you need to know that the oxidation reaction always happens at the anode. I remember that by anox. Oxidation always happens at the anode. So since zinc is being oxidized, that means this zinc bar is our anode. Anox. I also remember it because A is a vowel and O is a vowel. Yeah, for real. I really remember it that way. Reduction always happens at the cathode. Red cat. Again, this is a consonant. This is a consonant. I really do remember it this way. Oxidation happens at the anode. Reduction happens at the cathode. So this is a cathode, this copper bar here. What else do we need to know about a galvanic cell? Well, electrons are going to flow from the anode to the cathode always and forever. It's all about the alphabet today. I remember that A comes before C. So anode to cathode, electrons flow through the wire from the anode toward the cathode. This is electrons flowing up here in the wire. What else do we need to know about a galvanic cell? Well, as electrons flow through this wire from the anode to the cathode, the reduction reaction happening over here at the cathode causes extra copper to be deposited on your cathode itself. Because the copper ions are becoming solid, they get deposited directly on the cathode. So the cathode actually becomes heavier over time. It accumulates extra mass from copper solid being reduced there. On the other hand, what's happening at the anode? The anode is actually starting to dissolve in solution because the anode solid is becoming extra ions. You're actually losing mass from your anode as your electron flow continues. So the cathode gains mass while the anode loses mass. Just a little bit more about a galvanic cell. When you set up copper solid and copper ions in a beaker, and zinc solid and zinc ions in a beaker, and you connect them by a wire, no current will flow through that wire unless those beakers have another way to communicate. And that other way to communicate is through a salt bridge. A salt bridge contains spectator ions, 2 spectator ions that are a salt. Why spectators? Because you don't want these ions to cause extra confusion in your oxidation and reduction reactions. You want these ions to not participate in your oxidation reduction reactions. The purpose of these ions is to maintain your beaker solutions at electrolytic neutrality. Oh, what? These ions are going to travel one way or the other to maintain electrically neutral solutions in your original beakers. Let's try to explain what that means. As this zinc reaction is happening at the anode, you're starting to accumulate, or you would start to accumulate, an extra positive charge in the beaker because you're generating extra zinc 2+ ions. But a solution cannot have a positive charge. So chlorine ions, or your anion, whatever it may be, on the salt bridge, chlorine ions in this example, are going to start flowing into your zinc beaker from the salt bridge. Because if they didn't, this zinc solution would become positively charged. So chloride atoms move in to maintain electric neutrality. Anions always move toward the anode from the salt bridge. Conversely, cations move toward the cathode from the salt bridge. Why is this? Because your copper 2+ is being removed from the solution. So this solution at the cathode starts to become negatively charged, or would start to become negatively charged, if the salt bridge weren't there to allow cations to flow toward the cathode. Anions flow toward the anode, cations flow toward the cathode. Yep. That was a lot to pick up on galvanic cells, but I think that's a pretty good summary of everything you need to know about them. We showed this equation on the last slide, and what we did was we took the reduction potentials that we were given from a reduction potential table, figured out which reduction potential needed to be flipped to figure out who needed to be oxidized, and so we came up with an oxidation potential. When you're looking for an oxidation potential has the opposite sign from a reduction potential. So you can find the E of the cell by adding reduction and oxidation half reactions together. You may see the formula written this way, where you add the cathode and the anode together. The cathode is the reduction reaction, so you pull that value straight out of the reduction potential tables you're given. The anode is an oxidation potential value, so you flip the sign of what you are oxidizing. If you look at a lot of other resources, you may come across this equation instead of the ones above. I prefer the ones above just because I'm old and set in my ways, but this one below is also valid, but let me explain a couple of things about it. Both of these equations up top, this red E is an oxidation potential. And the way you get an oxidation potential is by flipping a reduction potential. And when you flip reduction potential, you have to change the sign of the reduction potential. So a flipped reduction potential, if it's a negative reduction, it's a positive oxidation. If it's a positive reduction, it's a negative oxidation. Yeah? That's flipping the signs and then adding. This equation down at the bottom, both of these use reduction potentials. The equation takes care of changing the sign for you. What the heck? If you had 0.34 from our copper earlier, minus negative 0.76 from our zinc earlier, minus a negative becomes plus a positive, you get the exact same value here as if you had manually flipped the sign yourself the way we did and then added them. I just don't want you to be freaked out when you see that there are some equations that add these things and some equations that subtract these things. You have to know whether you're using a reduction potential or oxidation potential. That was painful, but hopefully worth it. Okay, when we are asked about galvanic cells, like the one we've been working with, the Daniel cell that we've been working with, zinc and copper, a lot of those questions are going to ask us to find the cell voltage, or to find the cell potential, or to find the electromotive force. All three of those terms are the same thing to mean you're finding E naught cell. That's all. Cell voltage, electromotive force, cell potential, you're finding E naught cell. You're using reduction potential tables to figure out the E cell of that system. Electrochemistry is a useful type of reaction because you can harness the electron flow to do useful things like electricity and cell phones and a million other things. But not everyone in the world loves looking at reactions like this. I know you don't either. We could pretend a little bit longer. So we have come up with a way to write cell notation that you will see in places outside of chemistry. Let's look at this cell notation real quick. So we're looking at our same reaction between zinc and copper. When you do a cell notation, one of the first things to notice is that there's two tall lines in the middle. Those two tall lines represent the salt bridge. The salt bridge separates the anode from the cathode. It separates the oxidation reaction from the reduction reaction. I told you it's all about the alphabet this time. Oxidation comes before reduction in this cell notation. O comes before R alphabetically. Yeah, for real. So in this cell notation, oxidation comes first. And in our Daniel cell, what was being oxidized? Zinc. So we've got zinc solid becoming zinc 2+. And it's specifically 1 molar zinc 2+. My slide told me so. This solid should be separated from this aqueous by a solid, a tall straight line known as a phase boundary. What's happening at the cathode? What's happening on the reduction half? Copper 2+, aqueous copper 2+, that is 1 molar, is becoming copper solid. Are those different phases? Separate them by a tall straight line. So this cell diagram is one of the simplest that we will see, but they always have two solid things on the outside because the anode is always the very first thing you see. The actual physical anode piece is the first thing you see, and the cathode is the very last thing that you see. Not all reactions that we will discuss happen between a solid metal becoming metal ions or a metal ions becoming solid metal. We're going to see some reactions where they happen in gas phases and liquid phases and lots of things. So sometimes you have to have an alternate metal, an alternate thing to stand in as the receiver of the electrons or the acceptor of the electrons so that they can be transferred from one side to the other. So here's a different galvanic cell. This is zinc reacting with hydrogen gas and H+. Because we already see electrons, the arrow of electrons on this wire, we know that electrons are flowing from the zinc toward the hydrogen. I know that this is my anode and this is my cathode because electrons always flow from the anode to the cathode. The anode is the negatively charged electrode. So you see this little negative here. The cathode is a positively charged electrode. So oxidation is happening at the anode. That means losing electrons. Zinc is losing electrons. So zinc is becoming zinc 2+ at the anode. It must mean hydrogen is being reduced. So at the cathode, hydrogen is becoming H2. This H+ from HCl is becoming H2 gas. Sum those together and you get the whole reaction that's happening in this system. This system over here on the right is a very common system. It's called the She, the standard hydrogen electrode. The She, standard hydrogen electrode. The She is actually the reference point for all other reduction potentials. So the She has been established as having a reduction potential of 0 volts, and everything else is measured in reference to She. If we write a quick cell notation for this system, we can start with our salt ridge. The anode comes first, so that's zinc. Phase boundary to aqueous zinc, that's 1 molar. And then the reaction happening at the cathode is H+, that is 1 molar, is becoming H2 gas, that's 1 atmosphere. They're still separated by a phase boundary because it's aqueous and gas, but there's another phase boundary over here because your actual cathode reaction does not involve any solids. You have to have a stand-in electrode to be the receiver of electrons from the anode. And the receiver in this reaction is platinum. So platinum solid is our actual cathode. Does platinum participate in the oxidation reduction at all? No. The oxidation and reduction is happening between zinc and hydrogen, and platinum is just there to accept the electrons that it will then transfer to the hydrogen. Here's what it looks like, typed out all nice. If you can't read my handwriting, you are not alone. One final note. We've seen now that hydrogen has a stand-in electrode. There are other systems that have stand-in electrodes, and you will be told what those are when they appear. But this hydrogen is still an aqueous and a gas, so we still have a phase boundary. If you're ever trying to write a cell notation of two things that are aqueous, for example, iron 2 plus becoming iron 3 plus, those are both aqueous. We separate those with a comma, not a bar. So this is an oxidation reaction. It would be salt bridge over there, and there would be some sort of electrode over here. Platinum is often a stand-in electrode because it's inert. I think we've covered enough for now. It was fun.